Okay, let's start our chapters on weather and weather theory. This happens to be one of my more favorite. This is probably one of the most favorite topics in aviation for me, just because I'm kind of a weather geek. I think it's interesting just how weather works. There's aspects of it that are still kind of, I'm still in discovery mode on, still learning a lot about weather. But the more you understand about how weather and weather patterns work, the safer pilot you will become, the better decisions you can make. And so the next several lessons here, we're going to talk about weather theory. So our first session, we're going to focus just on the big picture, what causes weather? Why does weather patterns exist? What causes them? What are the major high-level factors to create the weather that we see every day? So we're going to jump right in. And the highest level you can go on weather as far as the reasons we have our weather patterns is the sun. The sun and the heating of Earth and its atmosphere is really the sole purpose of why we have weather here on Earth to begin with. The changing weather patterns day in and day out are a direct result of Earth's heating and cooling cycles that occur within the atmosphere. And of course, the heating cycle caused by the sun itself. And so as you can see, one of the major themes we're going to talk about is the constant churning of the atmosphere, the constant rising and sinking of Earth's atmosphere as it heats up and it cools off. The question, the main question on your written test and potentially during your oral exam will be what causes weather on Earth, and it's simply the heating and cooling of Earth caused by the sun. If we peel the onion back a little bit and step a little deeper and study the flow patterns of the atmosphere around Earth, we're going to find that something that we call circulation, static and distorted circulation, occurs within the atmosphere as Earth spins and rotates around the sun. Hot air, of course, we know hot air rises. Anybody who's maybe has a two-story house here in Texas, when it gets really hot in the summertime, knows that you walk upstairs, maybe your air conditioner's not running. Your upstairs will be warmer than your downstairs. And we all learned back in the day that hot air rises. And more specifically around Earth, hot air actually rises and flows around the Earth, down from the equator around to the poles. And just from a physics perspective, anytime a void is left, as hot air leaves a certain volume of space, that space cannot remain airless. It creates a vacuum. And so air rushes from other locations to replace the air that has left that space. So if we think about go back to the example of your house. As air heats up downstairs and rises, it moves up to your upstairs, but the volume of space downstairs that was vacated by that now warm air will be replaced through a vacuum. That the air will rush to replace that vacated air, and the cycle continues. And that's essentially how weather works on Earth. Earth's rotation adds an element to the way that we see weather patterns on Earth through what we call Coriolis effect. This is a distorted pattern that is caused by the fact that Earth's surface is a friction environment. And if you can imagine Earth's atmosphere being a fluid around Earth's surface as the surface of the Earth spins at quite a high rate of speed. You'll notice that the atmosphere around Earth's surface reacts to that friction environment and actually deflects. And if you're in the northern hemisphere, it's going to deflect to the right, and if you're in the southern hemisphere, it's going to deflect to the left, deflecting towards the equator. And this is called the Coriolis force, another flow pattern that causes the weather patterns that we all see here on Earth every day. Now, we're going to take one step deeper and look at how these flow patterns actually start to create the weather that we see. And we're going to do this in the context of pressure systems. Pressure systems are simply a result of the rising and sinking patterns that that are caused by, effectively caused by the heating and cooling of the Earth. And so let's look at our low pressure system here. You can see our low pressure system is an area of rising air, which we've already kind of defined as the heating of Earth's surface. So the heating of the air at the surface will rise, and as that air rises, I mentioned a vacuum is created at the surface. So here at the surface, we've got a vacuum. And that vacuum is what we call an area of low pressure. As if you have a volume of space, a vacuum will be a lower pressure than a volume of space near it that does not have a vacuum. And that vacuum space is quickly replaced by air from an adjoining region. So over here to our right, area of high pressure, you can see it quickly replaces the air in the low pressure region. And so this is a constant cycle. Air warms up. Let me actually grab a pen. Air warms up. It rises. A vacuum is created. Air from an adjoining region quickly, instantaneously replaces that air, and the cycle continues. The high pressure area is an area of sinking air as a space or a potential vacuum is now filled with air, its pressure rises. And that sinking air will generally be the source of air that replaces our low pressure system. And the cycle continues. This is ultimately what creates wind. So as I sit here in my house, here's my little stick figure. The wind that I feel day in and day out is that cycle of air replacement from areas of high pressure to areas of low pressure as the cycle continues. Air rises, air comes to replace it, the air has to go somewhere. One more note on high and low pressure systems, and this is something you'll see during your FAA written test and potentially during your flight test. Areas of air pockets that are circulating clockwise and they're diverging and they are sinking are areas of high pressure. Anytime you're thinking about high pressure, you're thinking about divergence, sinking air, clockwise rotation. That's high pressure. Air that circulates counterclockwise or is converging or is rising is an area of low pressure. And if we go into a different hemisphere than the one we're in now, say the southern hemisphere, all these directions will be opposite. So it's just something to keep in mind. When you're flying in the northern hemisphere, all your circulations, your clockwise circulations are high pressure systems, your counterclockwise circulations are low pressure systems. And this is going to make a connection to the type of weather we will expect to see in these areas of high and low pressure regions. So at this point, all we want to remember is high pressure regions are areas of clockwise circulation, diverging, and sinking. Low pressure regions are areas of rising air, so we can think of heating, right? Air is heating, it's rising, it's a counterclockwise rotation, and it's converging. All right, now that we kind of understand how the Earth is heated by the sun, how the pressure systems are a direct result of that, how air rises and it sinks, and how Coriolis effect kind of plays into the flow of weather around the surface of the Earth, we're going to start a discussion on stability, because all of these things, the rising air, the sinking air, play into how stable is our atmosphere. Let's start off with a couple definitions. So the international standard definition for a standard atmosphere, both by temperature and pressure, are 59 degrees Fahrenheit, which is 15 degrees Celsius for temperature, and for a stable atmosphere, our temperature lapse rates, which is the change in temperature as we go up in altitude. The definition of a standard stable atmosphere lapse rate is a decrease in temperature of 2 degrees Celsius per 1,000 feet. And so in a stable standard atmosphere, 2 degrees per 1,000 feet. And what we're going to find is, as our atmosphere becomes less and less stable, so hint, think thunderstorms, as the stability of our atmosphere decreases, the lapse rate is going to increase. So 3 degrees per 1,000 feet, 4 degrees per 1,000 feet. God forbid you see 5 degrees per 1,000 feet. That would be an extremely unstable atmosphere. So if anybody asks you, hey, what is the standard lapse rate for a stable atmosphere? You're going to tell them, well, that lapse rate is a change of 2 degrees per 1,000 feet, 2 degrees cooler per 1,000 feet. And of course, the faster the temperature drops, the less stable it is. And we'll go over a little bit more of that in a minute. You can have what's called a temperature inversion. So, for example, in a standard atmosphere, on a standard day, in a standard situation, you're going to have a temperature of 15 degrees Celsius at the surface, which will turn into a temperature of 13 degrees Celsius at 1,000 feet, 11 degrees Celsius at 2,000 feet, 9 degrees at 3,000, so on and so forth. And so that is our standard atmosphere. And so that's the picture here in the left. So you've got warm air, and it cools as you go up in atmosphere. A temperature inversion is one in which the air does not cool as you go up in altitude. So if you're flying along and you notice that at the surface it's 15 degrees Celsius, and at 1,000 feet it's 18 degrees Celsius, and at 2,000 feet it's 20 degrees Celsius, you have flown into a region of what we call temperature inversion. So it's just inverted to what the standard atmosphere is typically exhibiting. And this is generally a good thing, because as I noted earlier, as you go up in altitude, the more your temperature drops as altitude increases, the less stable your atmosphere is. In other words, the more likely it is that you're going to generate thunderstorms and other, other weather phenomenon that you're not going to want to fly in. But if you're in an atmosphere that actually warms up slightly as you go up in altitude, this is generally very favorable. We call this temperature inversion, and it's going to generally bring very favorable weather conditions. Why? Because the temperature of the atmosphere as it goes up is not favoring a fast increase in expansion or air moving from the surface upwards. Remember we talked earlier that warm air at the surface is going to rise? Well, if we've got warm air at the surface, let's say we've got air down here that's at 15 degrees Celsius, if it rises and meets an air that is actually warmer, let's say 20 degrees, it's not going to rise anymore. It's going to stop right there. It's not going to have the ability to rise anymore because it's met a pocket of air that's actually warmer than it is. And so this is generally a good thing. Remember, if we go back to our picture of rising air in our low pressure system, low pressure systems generally bring poor weather conditions, thunderstorms, rain, poor visibility, because the air is rising. And we're going to get into some more of that theory in the next lesson. But it's very important to notice that if we can stop that rising air through a temperature inversion, you'll have more favorable stability, more favorable weather conditions. We'll go into more on how that can affect, how stability can affect your weather here in the next lesson.